although you will not see it really in the breakdown of the content areas that you need to learn. So if you go and look in your SAGs, please, it's an important document. I keep on saying it. You will see that kinematics is 50%. So it makes up 50 marks, 25%. It makes up 50 marks of your final physics paper, which is quite a lot. And vectors falls under kinematics. So it's still there, even though you don't see it there in the breakdown, you will always get vector questions. So if we look at the definitions, remember a vector has magnitude and direction. Now, most of the time, the first question in your physics paper, and you'll see when you go and look at the past paper questions, is it will give you a bunch of quantities, and then you need to decide, are they vectors, are they not vectors? So make sure you know what a vector is and what a scalar is, because a scalar will only have a quantity and not a direction. So please, a size and not a direction. Now, a resultant vector is where we need to start talking. You must be able to draw vectors. And we've been drawing force diagrams since you were in grade 8. So when we're drawing a force diagram, and we're actually only going to ever ask you for a free body diagram now, you're going to draw your object as a dot. And then when you draw the vector, please make sure that you show the direction of the vector by using an arrow. If you don't have an arrow, it's not a vector, because this part shows the direction, and the size of your vector will indicate the size of the whatever quantity you are measuring. If it's force, most of the time it's going to be force, but it can be velocity or anything else as well. Any vector can be represented as a vector diagram. Now, the next thing is we are going to use north, east, south, and west to indicate the direction of a vector, or we're going to use bearing. Now, the first thing with north, east, south, and west, you cannot just say northeast. So when you have a vector that's going in this direction, for instance, you cannot say northeast because we don't know what the exact angle is. So when you state the direction of a vector, you need to state it in relation to the angle, always. So if this is our angle theta there, then you have to say that your vector, now think about it, it's moving towards the east from the north. So it's going to be theta degrees east of north. Okay, so just quickly revising. I'm not going to do examples really of this. If this is my theta here, you're going to measure from the east, and I'm moving towards the north. So that will be theta degrees north of east. So this is mainly what you're going to get, but they can also give you bearing. Now, what is bearing? Bearing is often used in geography as well. And in geography, you would have learned that where north is, it's going to be on a bearing of 0 degrees. And we don't use the same method as in maths. We go around clockwise. And once we've completed a full circle, we've done 360 degrees. So when we here, it will be 90 degrees. When we here, it will be 180 degrees. And when we on this line here, it will be 270 degrees. Now, you don't have to say north, east, south, and west then anymore, because if this is my vector here, you measure all the way here, and you're going to say at a bearing of, and then if you have an angle, for instance, of 20 degrees here, then it's 90 plus 20, so it's going to be 110 degrees. So you need to actually state the direction of your vectors. There's normally at least one question in a paper on this. Now for a resultant vector. Resultant vectors is a vector, according to the definition, that has the same effect as all the other vectors acting together. Now, I can't see them asking you a scale diagram ever, but what you need to know is if I have then, I don't want to use a dotted line, let's just take that away. If I have a vector that goes this way, and then I have a vector that goes this way, and then I have a vector that goes this way. So say it's someone walking. Now you need to remember that the resultant would be the vector that from the start of the first one replaces the effect of all these vectors, because that's where I'm going to end up. So my resultant vector is going to be in place of all of those. Now, normally you're not going to get so many of them, and you're only going to have two vectors, for instance. So if you are running across a field, they would say a person is running north, for instance, and then the person is running east. What is the resultant vector? Now, please remember, if this, I'll get to forces now, but if this was a force, you still need to, even though it's going from the same point, when you want to get the resultant vector, if there is a resultant vector, you're going to always draw them one after the other. We call it the head to tail method. And this vector that replaces them or has the same effect will then be our F net, or our resultant force. Now, if it was, or vector, doesn't have to be force. So if it is a force, so if you have an object here and you now have a vector pulling it north and a vector pulling it east, please think about this logically, because if you're pulling this way and this way, the object must end up going somewhere in that direction. It cannot go there or there. And these are the options that people choose often because they don't focus on the question. And this is why I said you have to take them. So if this is vector 1 and this is vector 2, you have to take them and redraw them one after the other. So I need to take that vector. You can move it anywhere if you want. You must just keep the direction and the size the same. And then I take vector 2 and I draw vector 2 after. Now it doesn't want to play nicely, but let's just redraw vector 2. And one after the other. From this one's head, the other one's tail would start. And then your resultant would be from the start of your first vector to the end of your last vector. So the components that makes up the resultant will never have an arrow next to each other, but the resultant will start at the tail of the first one and end with at the head of the last one. So that's going to be our resultant. Now remember, normally you're getting 90-degree angles. So if it's a 90-degree angle, you can use Pythagoras to work out this. So you're just going to say r squared is equal to 1 squared plus 2 squared. But when you get something like this in an exam, that's not enough. You'll get half the marks because you have to state the direction. So you have to say then that my theta I can go and calculate by using any trig function, but normally it's easiest to use opposite over adjacent because normally you have those two components. So you can say that tan of theta is equal to, in this case, it would be 2 over 1, and you go and work out what theta is, and it must give you the angle. You know how to use your calculators, I hope. Just shift tan and you put in the value and you get your angle. But then the angle is not enough. If they give you the question as north, east, south, and west, you have to say theta angles east of north. Okay, if you're not sure how to do this, please go back and practice the examples in your notes again. Now, the one that is the most important is taking a vector and resolving it into components. So if I have a vector pulling in a specific direction, so I have a box lying on the floor here, and this box is being pulled in that direction. Now, in all the other sections, what you're going to need to do is split this up into horizontal and vertical components. You can call it X and Y if you want. It really doesn't matter. But what is important is that we normally want to know what is the component in your X direction and what is the component in your Y direction. Now, again, you can use your normal trig to get this, but you need to get your triangle right. Remember, this angle here is the angle with the horizontal. So if you're working it out here, you need to state with the horizontal if that was your resultant. But now in this case, we're going to say this is our x component or our horizontal component. So F horizontal, if this is my force F, the horizontal component of F would just be the part of F that's pulling in this direction. Now, if you look at the trig, it's going to be the adjacent side to my angle. So if I want to this, I'm going to say FH over F is equal to adjacent because theta. You don't need to know complicated trig, but this you need to know. So that means to get the horizontal component, in this case, please always go and look where your theta is. Just don't say horizontal is always cos because it's not true. So F horizontal is going to be F cos theta. And then you can calculate it. If they're asking you for the vertical component, that would be this component here. So it doesn't matter if you calculate it here using this triangle or you calculate it here using this triangle. Just remember that this angle then would be 90 minus theta. So a little bit of math that you need to do. So here, F vertical will then be, if you look at it, it's opposite over hypotenuse. So that will be F vertical over my F would be sine of theta. And if you simplify that, you know that F vertical is then F sine theta. Okay, components are important. Now, if they say something is in equilibrium, now this is super important because this comes up everywhere. If they say that an object is in equilibrium, what you know is that all the forces that pull this object up must be equal to all the forces that pull the object down. All the forces that pull the object to the right must be equal to all the forces that pull the object to the left, because otherwise it cannot be in equilibrium. Now, what does equilibrium mean? It does not just mean that velocity is zero. Yes, it does mean when velocity is zero, it is in equilibrium, but also remember, if velocity is constant, there's also no resultant force. So then it's also in equilibrium. Please look out for the sentence velocity is constant because then you know this is true. And F up will be equal to F down, all the forces up, and all the forces to the, that's the right, will be equal to all the forces to the left. Please, that's important because now if they're asking you for, if they give you a diagram and you have an object that's hanging here and you don't know what the weight of that object is, for instance, so they say to you, go and get the weight of the object. So you know the weight goes down, but they say to you there's a force pulling this way. Let's make it at an angle, and there's a force pulling this way. You will see this in lots of our past papers, especially for grade 11. Now, if I look at this, please go and just show yourself these lines. Don't do them in solid lines. You can just do a dotted line because now what you need to do, and you don't have to do it on the same diagram, you need to think this little force here, F1, and this little force here, F2, is causing this to stand still. But this is F down. So it's not F1 and F2 that's causing it to stand still. It's only the upward components of F1 and F2 that's causing it to stand still. So this will be the vertical component of F1, and we normally give you an angle. They could have given you the angle here with the horizontal. Just make sure you do your trig correctly. So if I have my theta here, I can see that this F vertical of force 1 again is going to be opposite over F1. So when I go and work that out, I'm going to say F1 that over F is equal to sine of theta. You don't have to put that step in. You can go straight to F1 vertical is F1 times by sine theta. And on this one, F2 vertical is equal to F2 sine theta. It's not always sine. Please just look at your triangle. And once you've got these two components, you can add them together. So F1 vertical plus F2 vertical will now give me my F down. So forces up equal forces down. And sometimes there's an equation, there are two unknowns and they don't give you this. Then just go and use the horizontal components as well. So you'll have one equation for the horizontal components, one equation for the vertical components, and then you solve it simultaneously. There are many examples like that as well. Last thing, on a slope, please, you need to get these diagrams right. If I have a slope and I have an object on that slope, so here's my object chilling on the slope. There's always going, and we are talking about it just being stationary for now. You'll see in Newton, you're going to talk about it when it's moving as well. But now let's just say it's stationary. So therefore, you're going to have three forces. Please, only three forces acting on this object. Do not put components in a force diagram. So you've got your weight going down. So always, we can't escape that. You're allowed to use a W or you're allowed to use an FG. If it's on the information sheet, you can use it. Otherwise, you need to write a key if there are other forces. Now, this object is not sliding down, and it's not sliding down because friction is preventing it from doing so. So there's friction there. Now, if it was only these two forces, this object would be pushing down into the surface, which it's not doing. So there needs to be another force, and that is going to be my normal force. Please remember the normal force changes with the surface. If my surface changes, the direction of the normal force will also change. It's always going to be 90 degrees to the surface, and that's my F normal. So those are the three forces acting on an object on a slope. But now they're going to ask you, is this object sliding down? Now, you have an equation for friction already that we did in Newton, but I'll revise it when we get there. You can calculate the frictional force. And if the frictional force is bigger than the downward force, and we're going to get to that now, then you know the object will not slide. And if the downward force is bigger, then the object will slide. But if they exactly equal. So they'll have to tell you that the object is just not moving. Then you know that this upward force up the slope must be equal to a downward force down the slope. So what you need to do is then you draw a different diagram. If they asked you for a force diagram of 3 marks, you leave it clean. Then you go and you draw another diagram and you say, okay, fine, I have those forces. I could leave them, I guess. I have those forces there. But now they're asking me for the force that would make this object slide down. So yes, there is a force down here. Or they can ask me for the force that pushes the object into the floor here. But you will see that those two forces are just components of the weight and you're not allowed to draw them in a force diagram. And what's way better is if you draw them as a little triangle, and because you want to have a triangle so that you can use your trig better. So I'm just going to move this to the other side there. So if that's my weight has a component that pushes it onto the floor that is perpendicular to the surface. Okay. And then if the weight also has a component that would make it slide down, you could have drawn it there, it's parallel to the surface. But the reason why we draw it there is because this triangle helps us. You'll see that you can prove this triangle, because they normally give you this angle, and you can prove this big triangle similar to that small triangle. But all you need to remember is that the weight and your normal force or your parallel or perpendicular force, yes, so we're calling it weight perpendicular or FG perpendicular, doesn't matter what you call it, that force is going to be, that angle is going to be the same as this angle here, and this is going to be weight parallel. So if this object is in equilibrium, then you know that the size of this force is going to be equal to your normal force. And if the object is in equilibrium, meaning it's just not sliding, then we know that weight parallel is going to be equal to our frictional force. And here you can memorize them because they are always the same. Now, if you've got your triangle right, the cross one will always be cos because it's opposite over hypotenuse. So it will be W cos theta. And the the two little lines. Sine has a line in it, if I don't know if it makes sense, but the sine, I do that and then I remember that it's sine, but you can figure out a way to remember it. But or you can just always go and draw your triangle because that will always make sense. So opposite over hypotenuse, so that's going to be sine, is going to be double, so it's going to be W, sure, sine theta. And this is how you're then going to work out the forces on a slope. If the object is accelerating upwards, then friction isn't equal to wave parallel. Friction would be, then you need to go and work out other calculations, and that's where we get to Newton. So that is it for the vectors chapter.